Maybe you could put up the method of moments on the three
we can go through it quickly. I looked at that before I came over. Method of moments estimator for the unknown parameters in each of the following distributions. Poisson with rate parameter lambda. Well, one of the things that you could do is you could derive the first central moment, which is the mean, right? You know the Poisson density. So you can write down its likelihood. You can differentiate with respect to lambda and demonstrate to yourself that the population mean is the same as lambda. So that's A. B, the exponential with a parameter beta. I guess I'd have to go and look up what the exponential was, but it works the same way. You can write down the likelihood, differentiate the likelihood with respect to beta, and show that beta is some function of the population mean, or the other way around. Population mean is some function of beta and the data, and then solve for beta. C, the uniform on the interval. We already did that one. We did that one a little while ago. D, now there's another exponential example. You can write down the likelihood, differentiate with respect to theta, so that gives you the moment condition, and then you solve for theta as a function of the moment. Find the maximum likelihood estimators for each of the distributions in A through D. You also know how to do that. You set up the first order conditions and solve for the parameters. So there's a very close connection between method of moments and maximum likelihood, by the way, since they both have the same starting place. For each of the following distributions, determine whether it's a member of the exponential class of distributions by examining the log likelihood. Also, for each distribution, identify the sufficient statistics. Is the normal an exponential? Yeah, because we can get rid of the 1 over radical 2 pi sigma squared term. It just becomes a nuisance parameter. So we can separate it into a part in the exponent and some nuisance stuff that we can just forget about. How about y-ball, which is given there? Is the y-ball an exponential? Well, the log likelihood, you end up with you get the nuisance terms, log of alpha and log of beta. Forget about those because the only parts you need are the parts involving x to the beta minus 1 and e to the minus alpha x beta. So you can separate it out into those two pieces. Also for each distribution, identify the sufficient statistics. What does it mean for a statistic to be sufficient? What? Yeah, that's kind of an undergraduate explanation of a sufficient statistic. But there's a more formal definition that depends on the Blackwell theorem and separability. But, yeah, you have to be able to factor the density into two parts. One part that involves the data all by itself, and another part that involves the data and the parameters. And the parameters are here in the other part. If you can't factor it into two parts, where the unknown parameters are involved in their own piece, then you don't have any sufficient statistics. So because, for example, you can factor the normal into two pieces, where all the unknown parameters appear in one piece and nothing but data appears in the other piece, that's the mean and the variance are sufficient statistics. So the question is, then could you do the same thing with the y-ball? And the answer is no. Because when you write down the density and try to factor it, you end up with some unknown parameters in both pieces that you factored out of the density. You're always going to have those multiplicative alpha and beta terms. So that doesn't work. So we could factor the density that way, but then we've got alpha and beta off in the first part, and we've also got them in the other part that involve the data. And so alpha and beta are not, or your estimates of alpha and beta are not sufficient statistics. In the classical regression model with heteroscedasticity, which is more efficient, ordinary least squares or generalized method of moments? Well, what do you know about the Gauss-Markov theorem? What does the Gauss-Markov theorem tell us? The Gauss-Markov theorem tells us that if we have garden variety heteroscedasticity, then ordinary least squares is not estimated. However, if the heteroscedasticity is in the form, suppose that expected value du transpose is equal to omega. Omega is an n by n matrix and can be considered information, a set of instruments. And so we could construct a generalized method of moments estimator using omega as a set of incremental variables. That's z in the example that I was talking about in class. And so we set up the moment condition as omega transpose y minus x data equals 0. And so that we can then show by Gauss-Markov that that becomes a efficient estimator. So in that case, generalized method of moments beats ordinary least squares. If you constructed the least squares estimator of x transpose omega inverse x, or quantity inverse x transpose omega inverse y, then it would be a tie. Usually, generalized method of moments is not an efficient estimator. But sometimes it's the only estimator. Consider the probit model. Big phi, the probit model says the idea behind the probit model is to pick the so the idea behind the probit model is to pick the beta in the limit of integration that solves the integration problem. So you have a sequence of zeros and ones for the dependent variable. And so you can write down the likelihood function as the product of these integrals, and then we maximize the likelihood function. So that's the idea behind the probit. And a well-known result for the probit is that the expected value of y is equal to that integral, the cumulative normal probability distribution. So if this is a moment result, so if the moment result is true, and we have a set of instruments which are explanatory variables, then we also have that orthogonality condition. And so we can choose betas to make that orthogonality condition to have condition true. And that, in fact, that's how computer software is programmed. So in your computer software, y is a vector that's made up of ones and zeros. Either people bought a refrigerator or they didn't. The x's might include things like their household income, the age distribution of people in the household, and so on and so forth. And we evaluate the cumulative normal at the limit of the integrand, and multiply by the xi. So we choose the betas that make that orthogonality condition true. So there's, in computer software, it usually involves some kind of root search over betas to find the ones that make it work. Does that answer your question?